Hello, hello, hello. Then good afternoon, everyone. Let's go to start more on PD seminar. And today we have a pleasure to receive the Professor Nikola Kamburov of that will talk to us on phase free boundaries under theoretic constraints de la Universidad, from the University of Pontificia Universidad Católica de Chile.
Thank you very much. Thank you very much for the invitation. It's always a pleasure to speak before this audience. I'll tell you about recent results on a problem, on a pre-boundary problem that I really like. This is just the latest chapter in this long, old project that I've had in understanding solutions to the one-phase free boundary problem that are not necessarily energy minimizing. Okay. These are going to be joint results with my student, Jose Basulto from Católica. And I'll describe in a second what the one-phase free boundary problem is. But the appeal that this problem has for me is that there's a very, very deep connection to the of the one-phase free boundary problem to minimal surfaces. And yeah, there is an echo of the results that we have in the minimal surface literature living now in the free boundary. Okay, so what is the one-phase free boundary problem? It is one of the archetypal free boundary problems. So you're seeking a function, a u, which is continuous on some bounded domain, omega. Okay. You prescribe some fixed boundary conditions on, okay, it's D, this notation that I have here on the slides, on some bounded domain D. And you prescribe some data on the fixed boundary. And you're looking for this non-negative function. So yeah, it has two parts. It has a region where it's 0. Yeah. And a region where it's positive. And in the region where it's strictly positive, it satisfies the equation for harmonic functions, Laplace u equal to 0. Now, on the boundary of the positive phase here, this is known as the free boundary. Yeah, it satisfies, in addition, a constant gradient term. And note that, yeah, now on this, yeah, on the free boundary, the function is overdetermined. It's both 0 and 1. And so the free boundary is part of the unknowns of the problem. It cannot be just fixed in any place because you would get an overdetermined PD. Okay, and this, yeah, free boundary, this problem is very nice. It's scale invariant. So if you have a solution and then a rescale of it, say to the URX, yeah, solves the free boundary problem in the rescale domain. Okay, D divided by. Okay. Yeah, it appears in models of in combustion theory, in fluid mechanics, in optimal insulation, in electrostatics as well. And it's not, another nice thing about it is that it has a variational nature. So these are precisely the Lagrange equations for the following functional, in which we have a gradient square term and a potential which is discontinuous. The potential is the positive, is the characteristic function of the positive phase. Okay, and it's precisely this discontinuity here which gets translated to the free boundary condition, the constant gradient condition. Okay. So yeah, the functional here is now called the Alt-Caffarelli functional. in honor of Alt and Caffarelli, who were the first to systematically study this problem. And in a groundbreaking paper from 1981, they studied precisely the minimizers of this functional, and they proved many things, among which one, the minimizer satisfies the free boundary problem in a certain weak sense. Okay. Now, yeah, the regularity of the minimizer is intimately related to the regularity of the free boundary. So by studying the regularity of the free boundary, at the same time, you also get better and better information about the regularity of U. And what they showed was that the free boundary is a smooth hypersurface. Yeah, well, except yeah, there is a set, a relatively close subset of n-1 Hausdorff dimension 0. Okay, the free boundary is rectifiable. Another language. And on the regular points of the free boundary, actually the solution, this energy minimizing solution, satisfies the problem in a classical sense. Okay, so you have constant this gradient, constant gradient condition satisfied from one side, from the positive side. Yeah, well, their paper revealed this fascinating analogy between that I alluded to between this problem and another scale invariant object, which is minimal surfaces. Okay. And this initial, I mean, for example, the regularity theory of Alt and Caffarelli of the free boundary mimics very much the regularity theory for area minimizing minimal surfaces of the geometry. It uses the same tool set. And yeah, the paper gave an impetus now to just, yeah, apply results developed and techniques developed from the minimal surface world to the free boundary, world. Now, our best understanding of, for example, of the singular set is that it is a set of Hausdorff dimension at most n-5. And this result is just a consequence of techniques, the kind of the nature of which were developed for minimal surfaces, things like monotonicity formulas, dimension reduction techniques, all of them now in the hood of geometric measure theory. Okay. Well, as I mentioned, I'm interested in solutions of the one-phase free boundary problem that are not necessarily energy minimizing. Okay, and I'm, yeah, from now on, when I say solution, I'm gonna mean a classical solution. Really, you have just a free boundary that is smooth. On the one side, the solution is 0. On the other side, it's positive, and you have the constant gradient condition 1 on the free boundary. Yeah, but you're not going to assume anymore that they minimize the energy given the fixed boundary conditions. So, yeah, what can you say about the shape of the free boundary, say on an interior scale? If you have the one-phase free boundary problem defined on a ball of radius 1, yeah, what does it look like on a ball of radius 1/2? Okay. And in particular, you want to understand, yeah, if you have like points of high curvature, the solution is flat. Really, just what can you get about the shape? Well, this is a much broader problem, so you need to limit a little bit your focus. And one perspective is to study these general critical points of the functional under a topological constraint. For example, this approach works very well in low dimensions. You could study, what would the shape of the free boundary be, or of the positive phase of the solution be, if the positive phase is simply connected. Okay. Yeah. Another approach is Well, okay, I'm not gonna look at pure minimizers of the energy, but I do want to understand their, well, I want to limit the degree of their instability. Okay, so say I want to study stable critical points of the energy, or I want to study just finite Morse index critical points of the energy. Okay, so does this constraint impose a certain rigidity on the free boundary itself? Okay. Well, when you want to study this local problem, actually what you do most of the time is, especially if you're looking at possible points where the curvature could become large and large, is that you take rescaled, you take blow-up limits of these solutions, and you get a solution defined on the entire Rn. Okay, and then the problem, local regularity problem, really becomes a problem of classifying global solutions of the one-phase free boundary problem. So yeah, the results that I'm going to talk about will concern solutions, and I'll tell you how, global solution classification actually also tells us something about the local problem. So, right, let's start with global solutions under the topological constraints. And here I'm going to look at the start, it's just 2 dimensions, R2. So what are the global classical solutions of the one-phase free boundary problem, whose positive phase has finite topology? By that I mean the free boundary has finitely many components. Okay, so finite connectivity of the free boundary. Okay, so there are some obvious solutions. Yeah, there is the solution x, the positive part of x1, which I call the one plane solution. Now you can also double it up. Yeah, you could have a one plane here divided by 0. This is called the 2-plane solution. Yeah, another obvious solution is the disk complement solution. So the one coming from the fundamental solution of the Laplacian. Log, yeah, so defined, and now so it's 0 on the disk on the unit disk, and here it's positive. Yeah, well, the development in the subject really was really accelerated in 2011 by a paper by Oswert, Elani, Ipakar, in which they constructed a new solution, previously unknown, which we call the double hairpin solution. So it's a solution whose positive phase, guys, all right, very well. Its positive phase is bounded by 2 catenaries. Okay.
Sorry, am I misled to believe that then you can construct anything between given 2 minimal surfaces? If you prescribe somehow, because these are all minimal surfaces, right? So
what do you mean that they're all minimal? Yeah, no. There is this analogy.
And the hyperplanes and sphere, and they're all in CMC.
I'm going to explain this in a second, how the relation to minimal surfaces in 2D, that it is actually not just in the spirit, but very much in the flesh in a second. Okay. Yeah. So yeah, you have now these solutions, and the Oswert, Helland, and Pakar conjecture that these are the only ones in R2. Okay. And turns out that a finite topology. And turns out this is true, and was proved by Trezé. In a second, I'll show what give an idea what Trezé did. But yeah, just to mention something, this global classification result, we exploited in a couple of papers with David Jerrison. to prove local rigidity estimates for the one-phase free boundary problem, assuming simple connectivity of the positive phase. Exactly, yeah, this mechanism that I mentioned before taking blow-up limits. Yeah, you get from the local problem to the global problem, and in a sense, yeah, these are the models of things that happen locally as well. Right. So by the way, these are the only solutions modulo similarity transformations, precisely because you have the scale invariance here. Okay. All right. So what did Trezé do? So yeah, he related the solutions to the one-phase free boundary problem explicitly to minimal surfaces. So if you take a solution to the one-phase free boundary problem, which satisfies this gradient bound in the positive phase, then you can lift it to a complete embedded minimal surface, which is called it's a bigraph. It has a plane of symmetry, and each half of it is graphical. Okay. So yeah, then what turns out to be the case is that the counterpart of this complement solution is the vertical catenoid. Okay. And the counterpart of the hairpin solution is the horizontal catenoid. Okay. And Trezé did also the other direction. So if you start with a minimal bigraph, then you could get a solution to the one-phase free boundary problem. And by using classification results for minimal surfaces with actually two ends, classical results by Shane, he was actually able to prove that the only solutions that have finite connectivity, only three boundary solutions of finite connectivity has to be these and none else. At the same time, he also rediscovered a new solution. It was previously known in the fluid dynamics literature. It's just a train of hollow vortices, they're called. And they're the counterpart to the singly periodic short surface, which is a minimal bigraph. In fact, yeah, there's a one parameter family of these periodic solutions. Yeah, where you have the parameter essentially telling how big this hollow vortex is, the bubble of zero phases. Okay. So these are the only known global classical solutions in 2D, and there is a conjecture that these are the only ones, in fact. But this is a very bold conjecture. Yeah, it's a hard one. It's related to a hard conjecture in the minimal surface literature called the Shirk uniqueness conjecture. Okay, so what about 3 and higher dimensions? Well, what do you have? You have the 2D solutions extended in a constant fashion in the higher dimension. You have the bulk complement solution coming from just the fundamental solution of the Laplacian in higher dimensions. And then you have also axially symmetric solution, which is the analog of this double hairpin in 3 and higher D, constructed several years ago by Liu, Wang, and Wei. And in addition to these, you really expect that the added degree of freedom is a large variety of solutions. Okay, so the topological problem becomes a little bit trickier to study. So then you turn to the variation-theoretic approach to studying this problem. So the second variation of the Alt-Caffarelli energy is given by this this form here. It has a Dirichlet term, and defined. It's an integral. It's a bulk integral over the positive phase, and the other part of it is a integral. It's a boundary integral over the free boundary. Okay, so already you get two very interesting terms of different nature in the second variation form. And you define it, the natural space of functions for this. Well, they're they're C-infinity, they're compactly supported away from the fixed boundary, but you know, they're allowed to be they're smooth up to the free boundary. Okay, and yeah, they're allowed to take non-trivial values. I actually do want them to take non-trivial values. So, because with these functions phi, they give you the unit velocity that you move the free bound up and down, unit normal velocity. Okay. The H term is the mean curvature of the free boundary. That is the sum of the principal curvatures. So then, yeah, we're going to call a solution stable if the form is always non-negative. And the Morse index of U will be the largest dimension of subspace of this function space X, the test functions, on which the form is negative, strictly negative depth. Yeah. And since we're interested in global solutions, yeah, we're going to define, yeah, also the global index, which is just, yeah, the index when the domain is Rn. Okay. Okay, so I'm going to start first with some results on when, yeah, solutions are stable, or what do we know, what beautiful things happen when we study stable solutions of the one-phase free boundary problem that are global. Well, the best thing that you could hope for is that if you have a global stable solution, then you have a Liouville theorem for it, and that its free boundary is flat. Okay, meaning that, yeah, it's either the one in high D or the two-space solutions. You're either one or the other. And so I'm gonna call this a Bernstein type statement, because it's very much related again to what happened earlier for minimal surfaces. Okay. But a couple of years ago, we proved a theorem that if this Bernstein statement is true, is valid in dimension n, yeah, so the global problem is true, then the local problem, you get nice things about it too. You get curvature bounds of the free boundary. So if you have a solution to the one-phase free boundary problem defined in B1, again, classical solution, then the curvature on the interior scale is universally bounded, okay? Bounded by dimensional constant. In particular, yeah, the free boundary can be represented, each piece that a small disk, unit-sized disk intersects, say B116, is going to be the graph of a function with bounded C2 norm. So why do I use the moniker Bernstein? Well, there's the classical Bernstein theorem, which, yeah, in which you study complete minimal surfaces that are area minimizing, and they're known to be flat when the dimension of the surface is up to 6. Results of, yeah, Bernstein, DiGiorgi, Elmgren, Simons. Lately, there has been a lot of interest in what's called the stable Bernstein problem. So instead of wanting your surfaces to be minimizers of the area functional, you just want them to have non-negative second variation. So up to second order of the perturbation, the area does not decrease. So is a stable, complete minimal hypersurface hyperplane? Is it flat? And this is known to be true classically in dimension 2 by results of contemporaneous of Fisher-Colbury, Shane, De Carmo and Peng and Pogorelov around 1980. And only recently, the dimension started creeping up. Okay, so dimension 3 a couple of years ago, dimension 4, the beginning of this year, was announced by work of Choros and collaborators, really the ones carrying this breakthrough. And only a couple of weeks ago, mid-May, they reached up to dimension 5, work by, preprint by Mazet. Okay. So what do we have? What do we know in our free boundary world, free boundary mirror world? Well, first, let me tell you what do we know about energy minimizing solutions. Okay. So if you have a global solution that minimizes energy in every fixed ball, okay. The question is it just the one space solution, xn plus to rigid motion? And this is the case in dimension 2 by the work of Alt and Caffarelli, the original work. Then also in dimension 3 by Caffarelli, Jerison, and Koenig in the paper in which they derived the second variation form. And it is also now in dimension 4 by work of Jerison and Savin that I'm also going to mention in a few moments. Okay, it's no, the answer is no in dimension 7 and above, because De Silva and Jerison constructed first in 2009 a singular energy minimizing solution, which is homogeneous of degree 1, a cone, a free boundary cone, which, because it's energy minimizing, actually allows for desingularization procedures, and this is what was done in this paper by De Silva, Jerison, and Shagulan a couple of years ago. And the question is open for dimension 5 and 6. Okay, what about the stable Bernstein version of this problem? So if you have a global stable solution to the one-phase free boundary problem, is the free boundary flat? Are you this guy or this guy? Well, in dimension 7 and above, no, because we have these non-trivial energy minimizers. It's true in dimension 2, and this is due to the logarithmic cutoff trick. You can prove it, not too hard. It's also known for dimensions from 2 to 5 if you assume axial symmetry. Right? Work by Fernandez Real and Rosoton. And it's otherwise open. Okay, so it's not even known if in dimension 3 you have the Liouville theorem that you have stable implies flat. So the first result that I'm gonna present is a partial result in dimension 3. Yeah, if we showed with my student Jose that if you have a global solution that is stable and its free boundary is a union of convex surfaces, then indeed the free boundary needs to be flat. Okay. So yeah, in particular, solutions that have bubbles of in 3D. So domain convex of 0, maybe like versions of well, convex unbounded components of zero phase. These guys do not exist. Well, not stable. They don't exist if you assume stability. This is ruled out. Okay, so a couple of remarks. What you always know is the free boundary is mean convex. Okay, so asking for convexity is not that much more. So it's always mean convex. The sum of the principal curvatures is non-negative. And yeah, this is the case because yeah, the mean curvature turns out to be is the other normal derivative of the gradient u at the boundary, and we proved in the paper that I mentioned earlier that we have this bound is always true, this sharp gradient bound, gradient u less than or equal to 1, if the solution is global. In fact, yeah, by the Hopf lemma, what you know is that either the mean curvature is everywhere 0 and you have a flat free boundary, or the mean curvature is always positive. So yeah, the theorem treats the case in which both principal curvatures are non-negative. So, okay, how much time do I have? 30 minutes? 35. Oh, okay, so I can even tell you a little bit about the proof of this. So the idea is to, again, very similar to what happens for minimal surface, is to plug in test functions which are based, well, in this case, on the Hessian. For the minimal surfaces is the second fundamental form. Okay, so you use test functions based on the powers of the Hessian. Okay, so when you integrate by parts, this guy in this, yeah, so you have your stability inequality, you plug in this, you integrate by parts, you get you know, a boundary term over the free boundary, and you get the bulk term. Okay, and on the right hand side is bounded by some, you know, gradient square term of the test function psi. Okay, and so now the game that you're trying to play is that you do want at least, well, you want both of these terms to be non-negative, the integrals on the left hand side. You also want them to be slightly positive, at least one of them. You have some extra room, and you want to make this as small as possible. Okay, so the point is that both of these curvatures actually, both of these terms contain information on the curvature of the solution. So the main tool is Simon's-like differential inequality that Jerison and Savin proved their classification result. So they used it for homogeneous degree 1 solutions of the free boundary problem, because they were interested in classifying stable cones. For us, yeah, we don't have that. So but we still have, you know, we don't get the best inequalities possible, but you still get some which are sufficient. So, well, yeah, what you can get, well, what you can infer from that paper is that the Hessian satisfies this, well, it satisfies a subsolution property, which in this case it has both two parts. It has a bulk part and it has a boundary part. Okay, and the bulk part tells you actually that, yeah, alpha powers of W are going to be subharmonic when alpha is at least a third. And then you have the boundary inequality fights in some sense in the opposite direction. And well, the best that you can get is that this coefficient beta that you want it to be as large as possible. Well, this beta is 1/2 in the case when both curvatures are non-negative. But yeah, the number is 2/7, much smaller, in particular, much smaller than 1. It's more than 1/3 when the curvature is allowed to change sign. And it's precisely this problem here that means that the method will not apply, because you want to apply it with some alpha at least 1/3. So the method won't apply in the case when both curvatures, when the curvature is allowed to change sign. Okay, so yeah, we actually used it for alpha equals to 1/2. This is what we did, and so then we had to worry about bounding this term here, and so you have to bound the Hessian. You have to get estimates of the Hessian, and there is an issue of integrability at infinity for just the integral of the L1, well, the L1 of the Hessian. Anyway, I'm not going to go further into more details. I wanted to give you a glimpse of the tools. Okay, so now what about the problem of, you know, finding Morse index? I'm going to allow I'm allow some degree of instability, just not going to be wild, just going to be bounded. Okay, so here, yeah, this this type of question was probably first asked by again in the minimal surface literature, in these fundamental results by Fisher, Colbury, and at virtually the same time Gulliver. So they studied complete minimal surfaces embedded in R3 that have finite Morse index, meaning that the second variation form of area is finite index. And what they showed is that in that case, the minimal surface has finite total curvature. In fact, finite total curvature is this estimate. It's precisely the integral of the second fundamental force squared is finite. And by classical earlier results of Osserman, when you have this condition, then you understand beautifully in topological sense what the minimal surface is. So it turns out that the minimal surface has to be conformally equivalent to a compact Riemann surface with some points removed from it. And moreover, if you study the Gauss map, the Gauss map is the map with the manifolds, each point of the manifold, and produces the normal vector to it, unit normal vector, which lives in the sphere. So this map, this Gauss map, extends past these punctures. It's a conformal map on the entire compactification of the minimal surface, and the index of the minimal surface depends essentially only on this Gauss map. Okay. Well, the basic stepping stone to proving this was the following proposition. It's in a sense a characterization of what it means to be finite Morse index. If the minimal surface has finite Morse index, then you are stable. First surface is stable outside a compact subset of it. Moreover, away from this compact subset, you could construct a positive Jacobi field for the operator, underlying operator. Okay. So what do we have in our setting? In dimension 2, this is the second main result that I'm going to present. If you have a global solution, define the plane, and we're going to assume that it has connected positive phase and finite index. And then just like for minimal surfaces, finite index implies finite topology. Okay. Well, now that you have, if you have finite topology, Trezet's theorem, Trezet's classification theorem, tells you that you can be only the one-plane solution, the discomplement solution, and the hairpin solution up to a similarity transformation, the double hairpin. In the first case, the solution is stable, and in the other two cases, the Morse index is 1. So if you're for the one-phase free boundary problem in the plane, you have 0, index 1, and then a jump to index infinity. No, nothing in between. Okay, so just like for minimal surfaces here, the basic estimate is a total mean curvature bound. Okay, so if you get a total mean curvature bound, actually you can easily get the finite connectivity of the free boundary. That's because in 2 dimensions, the mean curvature of a curve is just the curvature of that curve. Okay. So for example, you in 2D, we have in 2D, these do not write very well. Okay. So each bounded piece, free curvature, right? will have a contribution of 2 pi by Gauss-Bonnet, if you will, or interpreting curvature just by the turning of the normal along the curve. So you can't have infinitely many of these. You gotta have finite. And then the fact that it's the mean curvature is finite means that outside a big enough ball, big enough disk in 2D, the mean curvature is very small. So the turning is tiny. Okay. If you have an unbounded component, free boundary, strand, which is unbounded, then really, the turning of the normal cannot be too, and so you can get an honest sector of opening, essentially, well, pi minus, it's really bad, pi minus epsilon. Yeah, so you assume that outside a disk of large radius, this is epsilon. So yeah, if you have an unbounded component that is outside of this large enough ball, then it's going to contain a sector of pretty large opening. Well, you can't have more than 2 of these. Okay, so there are only, at most 2 of these infinite free boundary strands away from this ball. And inside, you could have only finitely many, well, bounded and unbounded, that cross this ball, in fact. So you gotta have, the finite connectivity. So yeah, invoking Trézé, you're done, save for the index computation. Okay, well, what are some other results relating? Where does this our result, where does it stand in the literature? Well, you have many results in the minimal surface literature relating Morse index to topology. The original works, the pioneering works of Fisher, Colby, and Gulliver, later Disk, Ross, more recently collaborations between Choros and Maxim. Yeah. For in the world of PDEs, there were very interesting works by Kowalczyk, Liu Packard, and Del Pino, and Kowalczyk, Packard, and Liu and Wei and Gui. In the past decades, in which they, in the context of studying finite-ended solutions of the Alenkhan equation in R2 in the plane, and in particular characterizing the 4-ended solutions as the unique ones of Morse index 1. A similar study was to these ones was done for there's a free boundary analog of the Alenkhan equation, which comes when you minimize the following energy, the gradient term plus this characteristic function of the interval -1 to 1. This is a degenerate double well. Okay, so you get a free boundary problem called the Bernoulli-Jett free boundary problem. Actually, this Bernoulli-Jett problem relates. It has very close connections to the one-phase free boundary problem, as well as to the Alenkhan problem. Okay, so we needed to study the quadratic form, and in particular the associated linear problem. And the associated linear problem, it's a Robin-Dirichlet problem. And we looked in the literature and we couldn't find this. Actually, we couldn't find the basic tenets of the theory of this. So we had to build it from scratch. But the theory, for the eigenvalues of this problem, just follows the same standard techniques, essentially, right? You do have, I mean, there's some subtleties in a couple of places, but most of the time it's just the standard arguments. So the eigenvalue problem has a discrete spectrum bounded away from 0 and infinity if you are working on a bounded domain, obviously. And the index in that case is just the number of the negative eigenvalues. Okay, you have the monotonicity value, the monotonicity property of the index. You can also, and it's useful to define an index not just on the positive face, which might have distinct components, but also you could study it on each connected component, and you get monotonicity there. And now, yeah, if the index of a global solution can be realized by the limit of indices over exhaustions of the entire space. Okay. And so, yeah, we proved along the way the usual characterizations of the index. Again, if you're a finite Morse index, then you're stable outside a bounded, stable outside a compact set, a large enough ball. You do get a positive Jacobi field away from the ball. You also characterize the index as follows. Yeah, if you have finite Morse index equal to say k, then yeah, there's a set of k orthonormal eigenfunctions to the problem associated with negative eigenvalues. Okay, well, this might seem obvious, but when you're working globally, it's not. In particular, it's not. What's not obvious is that these are L2 integrable eigenfunctions. Okay. So you have to do some estimates around here. And well, once you have this machinery developed, then proving the finite Stoll mean curvature bound is straightforward. It just uses the stability outside a bounded disk in R2. So the finite Stoll mean curvature is going to be you express it as an integral over a bounded disk and integral over the complement of it, where the solution is stable, and use stability to show that this is finite. Yeah, and the way you do it is by again using a logarithmic cutoff function, which is the nice object that you have in 2 dimensions. Okay, so at the end of the day, yeah, you get the finite Stoll mean curvature and you get a proof of the theorem. Okay, what about the index computation? Okay, so now this is a fun part. Yeah. So again, as in minimal surfaces, yeah, the index is going to be encoded in the geometry of, well, for minimal surfaces, it was the Gauss map. Here it's the G map, I call it, which is nothing but the z derivative, the complex z derivative of the harmonic function u. So in that way, you get a holomorphic function defined on the positive face. And this holomorphic function has very nice mapping properties. For example, the free boundary condition, okay, gradient equals 1, means that the norm of G is 1 on the free boundary. So yeah, the free boundary is mapped into the boundary of the unit disk. Okay. So when U is the complement of the disk complement solution or the double hairpin solution, what you know in addition is that this map is injective. So it's a biholomorphic map onto the image. Okay, and guys, let's draw them again. So this complement, and there's this complement, and then there's a double hairpin solution. So under G, yeah, the disk complement just goes to the unit disk minus the origin. And it's very, very easy to compute, yeah, because for the log, when u is the log, this g is just 1 over z. Okay, it's very, very easy. Okay. For the double hairpin, actually, the positive phase is mapped onto the entire interior of the unit disk. Okay. But now you want to see what happens to the free boundary. Well, the G actually extends as a smooth bijection to the closure of the positive phase. Okay. So, well, in the first case, the free boundary is mapped onto the boundary of the unit disk. In the second case, the free boundary is mapped to the entire boundary of the unit disk, safe for the points -1 and 1. Okay, so your solution, the positive phase plus the free boundary is just conformal to the unit disk, closed unit disk, minus 1 or 2 points. Okay, so now you could use the unit disk to parameterize the positive phase in both cases, and use this parameterization to rewrite the second variation form. And it turns out in these new coordinates, it has a very beautiful expression. It's just the Dirichlet energy minus the L2 energy over the boundary of the unit disk. So the curvature term converts into this. Okay. So you just have to study now the index of this form on the space H1. And why is this? Because, well, the index of Q, the index of the solution, which is the index of Q, defined on the space of natural functions, C infinity C, up to the boundary. Well, under so the pullback of this space is inside H1. So the H1 is a little bit bigger than the space of original test functions, but it's not that much bigger because these points, the ones that you excise, are of 0 H1 Sobolev capacity, so they do not affect the at all when you say you want to do some excisions around the singular points. Okay. So then you just have to compute the index of Q0 in H1. Note that, well, constant functions give me negative value, right? Okay, but now if I work modulo constant functions, and if I show that the form is negative, I win. The Morse index will be exactly okay. And now this is just very nice because, well, by the Dirichlet principle, I can assume that my psi's are harmonic. And now just like express everything in just harmonic modes. And each harmonic mode, which is of the form RK cosine K theta or RK R to the K sine K theta. When you compute the second variation, well, the gradient term can, by integration by parts, can be shown to be the same as a boundary term. It's just ek times the normal derivative of ek, and the normal derivative of ek just gives me k times ek. So in the end, I just have that this is k minus 1, which is non-negative when k is at least 1, and I have removed the 0 in the story. Okay. So this is the proof that is the index. And I have a couple more minutes. Oh wow, okay, fantastic. So I can discuss these and slowly. So just I'll end with a few open problems. Of course, the first open problem is really the stable Bernstein problem in R3, the full conjecture. Can you establish it? Okay, so it'll be great to get this result, but it seems, at least for the moment, that these techniques will not be enough to get there. So what about just global finite index solutions in R3, or just going one dimension higher? So we proved in dimension 2 that the integral of the mean curvature was bounded. This is in 2 dimensions, this is the scale invariant quantity. In 3 dimensions, the scale invariant quantity is mean curvature squared integrate. Okay, so does there exist an analogous total curvature bound for finite for global solutions of finite index? More broadly speaking, well, there are these results connecting the index to the topological features of the solution. And there, in the minimal surface literature, there are just these results which are very nice in the sense of you get estimates of the index in terms of topological features of the solution of the minimal surface, like the genus or the number of ends, etc. Can you get something to that effect in this setting for the one-phase free boundary problem? It coded in terms of the positive phase. Okay. And the final open problem I'm going to end with is just a very bold conjecture of that I believe is right, maybe 60-40 or 70-30. Let me call it 70-30. Okay. But at least at the moment I can't find a counterexample. So it is, remember, in 2 dimensions we showed that the only solutions of finite Morse index are just the complement of the disk, the hairpin, and the one plane. So this is something similar hold in 3 dimensions. So the only ones that are finite index and connected positive phase are the one space solution, the bulk complement solution, okay, and the solution, the axially symmetric solution by Liu, Wang, and Wei. Okay. So it would be I mean it would be quite a thing to prove this. I would be very, very, very happy. In particular, I mean this conjecture contains the previous one, so certainly. But there are just these fascinating problems that that at the moment don't have an answer in the free boundary world, that have obtained a pretty good and nice answer in the world of minimal surfaces. So, well, here I stop and I thank you for your attention.
Any question or comment?
Absolutely amazing.
Please.
About the Bernstein.
Mm-hmm. Yeah.
The deal with the concave counterpart.
Where was it? When both principal curvatures are positive, yes. Yeah. So the problem was the following, that I don't get, you see. So again, when I integrate by parts, these test functions here, so I get this boundary term, integral over the free boundary, and integral over the positive phase. And the game that you always play is that, so you don't want certain positivity inside of these 2 integrals, because that encodes the curvature of the free boundary. Okay, so the question is for which alpha these are going to be both positive or non-negative, but at least one of them positive. And so now, if you look at, say, the bulk term, this one? Well, yeah, by the just by this differential inequality here, the w times the Laplacian of w is at least 2/3. This actually means that w to the alpha is subharmonic when alpha is at least 1/3. Okay, so you don't want this alpha to be at least 1/3. Okay, but when the alpha is too big, okay, you get a problem with the following term here. Okay, because the normal derivative of w divided by hw, if alpha is too big, could be bigger than 1, and this becomes negative. So you lose the positivity of this term. So you get two integrals of different sign. Okay, and the best that you can do for the differential inequality on the boundary is that, yeah, that you have a constant, well, 1/2 when they're both of the same sign, and that works great for you. You could do it. But when one of them is allowed to be positive and the other one negative, which could happen, the best constant is 2/7. And this 2/7 is less than 1/3. Okay, so yeah. So you might hope, okay, I'm gonna use w to the 2/7. Yeah, and that will take care of this term. This is gonna be non-negative. But now this term is gonna be not necessarily positive. Okay, so there's a fight between these two differential inequalities. You know, each of them determines a certain range of the exponent. And when you're working in the regime that both are positive, you have a non-empty range for the exponent that you can take. Yeah, and if one of them, say, is allowed to change sign, then this, you know, range becomes empty. You don't have it. That's the issue. I don't know if I explained it to you. This is just, well, it's just a limitation of the method itself. So if you use a test function based on the Hessian, you're stuck with this. Of course, there could be different test functions, and not Hessian. It could be just involving gradient terms as well. Yeah, theoretically it's possible. Just that the computations now become extremely hard, and getting then the differential inequalities becomes almost impossible. It's very, very hard to compute. Yeah. Yeah, the conjecture, of course, is that it should be true no matter what the the convexity or concavity is. Yeah, of course. Yeah, it should be true always. But at least with this method, we could push it only this far. It covers only the convex case, fully convex. Okay. It could be pushed slightly further. So we could get it to get the Liouville theorem if you assume that the integral of the Gauss curvature is non-negative. Okay, so in that case, that's a little bit weaker, right? The product of the two curvatures, is globally, when integrated, is non-negative. That's a little bit weaker, but still, it's not the, it's not the Bernstein theorem. Yeah. Mm-hmm.
The same period, is that concept be the optimal, or do you know what is?
So for absolutely 2/7 it is optimal. Yeah. You just, there's a computation, and if the curvatures satisfy a certain ratio, and at a point, yeah, it's saturated.
To capture the decay or asymptotic behavior of the solution?
So in this problem, you do have to worry about, you see, the integral of well, this power of the Hessian. So you do have to worry about integrability issues in infinity. Absolutely. This is something I did not mention. So there is some extra work to show that this integral here. So again, I'm working in this regime, that this integral here could be made as small as possible. Okay, so there is work. I mean, yeah, this by Hölder inequality, you can, you know, bring it in two parts. One is completely in terms of W, the other one is completely in terms of psi. And then you have to just get some, you know, integral curvature, integral Hessian estimates to get the full theorem. Yeah. Yeah. Uh-huh. Um, well, that would be fantastic if you could prove that. If you could get some you know, symmetry there, definitely. But yeah, because then, yeah, if you say you get like axial symmetry or something like that, then I think the problem becomes much easier. You know, much easier, maybe even you know, very easy to do. But yeah, getting this symmetry, I don't know how to.
Then let's say thanks to Nikola again.
Thank you very much.
The restrictions that Kamburov was mentioning in his talk.
Was it?
The restrictions of concavity that Kamburov was mentioning in his talk.
Ah,
That's destruction because of those.
yeah. Yeah, no, but yeah, but this yeah, that's nothing to do in this case.